Hello everyone, welcome to the OpenFOAM webinar. Today's talk is given by Dr. Fatemeh Salehi. She is an associate professor at the School of Engineering, Macquarie University, Australia, and is currently a visiting associate professor at the University of Michigan, USA. She received her PhD from the University of New South Wales in 2015 and then worked as a postdoctoral research fellow at the University of Sydney before joining Macquarie as a faculty member in 2018. Her expertise is in the development of physical models for computational fluid dynamics, CFD simulations of single and multi-phase flows to advance new energy technologies. She is particularly interested in clean fuels such as hydrogen, ammonia, biofuel, and biomass. Dr. Salehi is a Fulbright Fellow and Executive Member of the Combustion Institute (ANZ), a member of the Scientific Advisory Board of Blue Economy Collaborative Research Center, and a member of working groups of Standards Australia for the development of hydrogen standards. Fatemeh, welcome your talk. It's your turn.
Okay, thank you very much, Bosen, for the nice introduction, and thank you for the invitation. It's a pleasure to be here. Today, I'm going to talk about particle-laden droplet-laden flows, which is one of the the projects we work for a couple of years on it. These sort of flow are relevant to a wide range of application from combustion technologies, if you're talking about liquid fuel injector, to the drug delivery technologies, agricultural spray, chemical reactor, and etc. And depending on the the application, the design requirements are completely different. For instance, in fuel injector for internal combustion engine, we require to come up with the technology that's droplet becoming small as much as possible, evaporate and mix fast. However, for the fire suppression, we require to generate droplets that can provide enough flux to overcome or suppress the fire. Usually, we're dealing with a complex series of interrelated phenomena, depends on the application and what we are interested. These include dispersion of the droplet or particle, surface growth or shrinkage, breakage, coalescence, agglomeration, and nucleation. So they are all connected and become quite challenging to model this sort of flow, which is the classification of multi-phase flow. As you all are aware, majority of these applications are turbulent flow. So basically, we can either use direct numerical simulation, larger simulation, or RANs. In DNS, just a very quick notes. So we're resolving all the scales. In larger D, we're only resolving larger scales and we're modeling the smaller scales. And in RANs, we're basically modeling the average. We are not resolving any scales. Since we're dealing with a type of two-phase flow here, there are two broad categories that we can classify simulations or modeling approach. The first one is the Eulerian approach, which in these methods define the cloud of droplets or particles by their velocity and concentration. So these approaches are mainly suitable for primary atomization, for dense particle scenario when we, for example, have a biomass process. We have another category we call the Eulerian Lagrangian. What we basically do in this sort of approach, we take in Lagrangian method for the liquid or solid phase, assuming they are dispersed. And then we track the dynamic of them, which are approximate as evolving points in a space. This sort of approach are more suitable for dilute spray regime, secondary breakup, and when we have a low load of particle flow. So today I'm going to talk about population balance equation. So PDF, or it's a techniques that consider the evolution of the particle number density in physical space and in property space. When we say property space, depends on, again, what we are interested. So it could be, particle droplet size, usually their volume, their shapes, surface area, morphology. So it could, we can extend or have a, a low dimension domain, depends on, again, application. Basically, the transport equation include standard terms. So we have the evolution of number density in time, and then we have two acceleration. So that represents with the acceleration or the velocity represented by the un side theta. So these are representing the velocity in physical and property aspects. For example, if we have evaporation, the side represents variation of the volume due to the heat transfer. And at the right side, we have the source term, which represent the net change of number density due to the discrete burst and death of droplet, which is caused by breakage or agglomeration. It's a highly nonlinear function of the interactive forces between carrier phase and dispersed phase. Again, this is a very general transport equation, and it becomes, quite complex and for analytical solution or direct solution. So the projects that we actually work on, it was motivated by secondary breakup in combustion devices, let's say, but secondary breakup are relevant to other, spray application as well. The experimental study by Barkormatsis and Masri shows that the shapes of the droplet are quite important. It's not only their size and shapes are important to characterize droplet, further downstreams. What usually models do in secondary breakup, they assume they're all spherical. What we try to do with the PDF population balance equation model is to account somehow for the effect of the shape of droplets. So since it's motivated by the secondary droplet, we consider our property space include two parameters or two properties. The first one is the size, and the second one is the shape. And we're focusing on non-evaporating spray. Basically, the third term will become, zero or not important. And we're going to end up solving, a more simplified transport equation. So this is the continuous equation. And when it comes to the LES, particularly when it comes to turbulence flow, particularly the source term, is become highly nonlinear and challenging to model. PDF or probability density function is the approach that we can take to address this problem. So we're using large eddy simulation for the carrier phase, which is here gas phase, and we're using a PDF version of the population balance equation for the dispersed phase. PDF version of the population balance is a continuous function, but its turbulence distribution is represented stochastically by ensemble of Lagrangian notional particle in the Monte Carlo simulation. Again, it's the standard basic concept of the PDF. So the challenge is that if you're looking at the, this problem, so in general, the number density represent a range of droplet size and shape with a very different slip velocity. We cannot present all droplet size and shape with a single PDF. This is because of the different trajectory that the droplet will take due to the inertia effects. So to overcome this, challenge, we actually came with the approach. We're going to divide the PDF PV to the, classes, and assume these classes represent the turbulence distribution of the number density of droplet that they have similar inertial interaction with the carrier phase. I'm going to talk about how we're going to come with these, classes, later. But assume we have these classes, and then we can write down the stochastic differential equation for each class, which is similar to the standard stochastic equation for droplets. So in this, formulation, we have two parameters that we require to calculate or somehow address. The first one is the particle response time, and the second one is instantaneous carrier fluid velocity, or the carrier velocity seen by particle. So this is because we're using the stochastic approach here. Tau p representing the mean across all the classes of droplet response time. This is due to the fluid droplet interaction, and it's actually a function of the drag force. So if we're assuming each class is limited to the droplet of only one size and one shape, basically this mean value or response time become equal to the response time of that particle size and shape. The equation that we can write is we're using the function, the relation between the tau p and drag force and slip velocity. The drag force is the function of the droplet size and shape. Again, since we want to somehow account for the droplet shapes, we're using the modified drag coefficient, which is defined based on Reynolds star that consider the shape factor. These shape factors coming from the experimental study is done previously by Luth and available for different shapes. The second one, as I mentioned, is to how we're going to estimate the carrier fluid velocity. So this is the instantaneous velocity or scene velocity by particles droplets. What we have from the LES is the filter velocity. So somehow we need to approximate the fluctuating component. So there are two broad categories. The first one is the approximation AMD, which is the approximate deconventional model. And the second group is the longevity model. There are different versions, so it could be very simple or very complex. Here we adopted a Pozorowski version that assume, a stochastic equation to compute the fluctuating component. So now it's about how we're going to identify the classes. So we have equation for each classes, but the key is that how we're going to identify these classes to ensure we're addressing the effect of the inertia. We adopted a method is numerical method and is based on Stokes, concept. Stokes is a non-dimensional number that somehow represent the effect of inertia. Is the ratio between the particle response time and flow response time. So a single notional particle represents a class of number density function without significantly compromising the accuracy of the droplet inertia trajectories. So we want to ensure we are not compromising the accuracy or somehow we addressing the effect of inertia. We can consider two extreme cases. The first one, when there is no inertia forces. For example, droplet size are very small and they basically evolving with the carrier phase velocity. In that scenario, solving the DFPB on ensemble of notional particle means each particle in turbulence will represent a single realization of the entire number density function. And we have a brute force option that we're going to have a notional particle that represent only one size and one shape. Basically, our method become essentially a point model for a droplet. We want to come up with something between. And for this purpose, we're using the concept of Stokes. So the way the model works is that we first establish the Stokes beams. We show them with the delta ST. That assuming the initial droplet have an approximately same dynamic response to the carrier phase. Delta ST is these Stokes beams are actually created prior to the simulation. And then we're going to have the initial particle representing a range of Stokes. We show it with the DST. So the criteria is that if DST is smaller than delta ST, it means that notional particle representing the droplet size that satisfy the Stokes criteria. In other words, representing the size that can be approximated by the same value for the response time. Then we calculate the average and we go to the next time. But if the DST is larger than delta ST or doesn't satisfy this criteria, as shown in the figure at the top, we need to split the notional particle. Again, it's the notional particle, and this is a numerical scheme I'm talking about. It's not a physical breakup. So as you can see, in the time 0, DST is larger than delta ST. So we're going to break it in a way or split it in a way that we have now two notional particle P and particle Q, but each of them satisfying the criteria. The particle will evolve based on the governing equation, and in the next time we go in again to check the criteria, and if any particle doesn't satisfy, we repeat this process. So the model implemented in OpenFOAM, we're using Eulerian LES solver exists in OpenFOAM, and the model is also compatible with MMC foam, which is the combustion solver lead and developed by University of Sydney. The first was to do some numerical analysis to ensure the model works. So for this purpose, we tested two different configurations. injecting the particle in line with the jet flow and injecting particle cross flow. So the aim of this configuration is again to assess the model, the framework. So we consider polysize but mono shapes, and also we consider polysize and poly shapes, and we assess the model performance against the point particle. We call it, droplet simulation here, that we basically, following each individual droplet. So the first step was to assess the convergence. So we can see that as we increase in the number of the stokes, so the model is initially sensitive to the number of the bins or stokes bin, but eventually become independent, and we don't see any, variation, which is true for both co-flow and cross-flow injection. We also look at to see if actually the model, has the impact. For this, purpose, we consider the extreme case, that assuming inertia or inertia effect is not important, and we can see a significant difference in both, mean diameter, velocity, and velocity RMS. The dashed line shows the result without the Stokes bin method, or if we use single PDF, represent all sizes. And we can see there's a significant difference. However, when we're using a Stokes bin, we get really good results with the point particle simulation. And we try to do also some validation against the experimental data. For this, first step of the validation, we use turbulence jet. Is the one-way coupling. We don't want to add complexity. Two particle size, 60 and 90 micron, and equivalent to the Stokes of 53 and 122 inlet Stokes number. So we can see that there is a really good agreement when you're looking at the results for the Reynolds number of 20,000. So the figure at the top shows radial dispersion, which is the mean square displacement of the droplet from the jet center line at a given axial location. And then we also check the velocity. So if we're looking at the velocity, again, for the 20K Reynolds number of 20K, we can see the agreement is really good. The red results, the results shown by red color. But for the 30K, we can see there's a slightly difference, particularly in the radial dispersion. But we are not necessarily blaming the simulation, because one of the the challenge was it also there are uncertainty relevant to the experiment. As we can see here, the experiment showed same level of dispersion for both sizes at 35 diameter away from the jet, which as noted by the experimental study, the calibration uncertainty is about 12%. Then we look at the polysize poly shape. So we consider two shapes. The initial particles are injecting with the same distribution, same size distribution, and we have a spherical and spheroid shape or oblate shape. So if we're looking at the figure here, they show size distribution at two radial location at 60 millimeter away from the jet. So the first radial location is at the center line, and the second is at the shear layer. We can see that how the shapes become important. So it's a very simple shapes we consider here, but even that we can see the significant difference between oblate and spherical shape. So again, to just highlight the difference. So basically, in the center line, we see that the span is wider for both shapes, as we expected. We have all sizes in the center line. But as we go to the shear layer, the smaller particle actually, because they're moving toward or they quickly adjust into the trajectory of the flow, the concentration or the number of the smaller particle is higher, which is can be seen with the higher peak. And also the span is smaller, so covering a smaller range, because heavier particle or particle with the larger Stokes, they stick to the middle. They're following their own trajectory, because all of them are actually injected from the center, but smaller particle, lighter particle, they quickly adjust to the flow, and that's the reason they move to the shear layer. And we can see that for the oblate shape at shear layer, the span is wider. This is because they have a shorter response time, and hence they have a, a higher level radial dispersion. We also did a simple test to see how the model works for the breakup, because the motivation was, of course, to come up with the approach or framework that can account for the droplet size and shape, but also come with the method that help us to have a better control on computational cost. In point particle method, what essentially happens when we have a droplet breakup, we don't have any control on computational cost, because the number of the notional particle or the point particle just increase as we have droplet breakup. This is a challenge for the Lagrangian method. But with this method, we have a much better control. So we adopted a very simple breakup model, again, to just emphasize that the breakup is the physical process, and notional particle splitting is a numerical modeling tools. So in other words, if you have a droplet breakup, it doesn't necessarily mean that we're going to split the notional particle. So droplet breakup happen because of the physical meaning. So here, for example, we consider it based on the Weber number and a frequency, a characteristic breakup time. But if it doesn't satisfy Stokes criteria, then we're going to split the notional particle. So we can see that again, the results shows with breakup and without breakup. So as we have breakup, we can see there is a significant difference. So the results also agree well with the point particle simulation, capturing the breakup, even it's a very simple model here. But most importantly, we found there is a significant reduction in computational cost. So the computational cost using PDF-TV was about 1/3 of the computational cost if we're using point particle method. Then we apply the model for more complex scenarios. So this is the polydispersed flow in a bluff body, and it's a two-way coupling regime. So the experiment was conducted by Bori group, and the particle size is from 20 microns to 100 microns. Mass loading ratio is 22%. It's the two-way coupling regime, which basically means the particle and droplet affect the carrier phase. So we first look at the carrier velocity for both single phase and two-phase flow. The impact of the particle is very clear on the carrier phase, as we can see the difference here. So the symbol shows experiment and the line shows the simulation. We can see that the modeling captured the physics, the circulation zone, or the negative velocity very well. There are some discrepancy when we actually have a single phase. There is the model is shows a slight difference, but which could be due to the initial boundary condition. But nevertheless, it's quite good. If we're looking at the particle velocity, for example, here we only showing the result for 20 and 80 microns. This shows the mean velocity and also velocity RMS. So with the simulation, we can actually represent the results assuming it's one way. So obviously this is not doable with the measurements, but with simulation we simply turn off the source stem. So it means there is no feedback from particle to the carrier phase. So we can see the difference if we comparing the green and blue lines. We can obviously say there is a difference when we confirming the impact of the two-way coupling on the particle evolution. And most importantly, we can see that these impacts are more significant for the smaller particle because they are more sensitive to the carrier flow. But the impact become, smaller for the larger particles since they are less responsive to the carrier flow. We also look at the mean distance from the center line. We see that the existence of a strong recirculation zone is obvious in these results. So there is a significant difference if we have a jet flow. In jet flow, we expected to see the distance or the dispersion increases as we go further downstream. But here we can see there is a increasing trend for all particle size except for 20 microns. The other thing is that the results were only available for 60 micron, the experimental result measurement. we achieve a good agreement, but with the simulation, we can see the impact on other particles. And it's interesting to see 20 micron shows a completely different trend. So it just shows the increasing trend, although for a larger particle, we can see the decrease and increasing trend, which is also consistent with 60 micron. So we later applied the model for a polydispersed jet. This is actually an experimental simulation, a study we did with University of Adelaide. With the measurement, what they can do, they're using PN and PIV measurements, which allows them to capture the mean concentration. So it's a very great techniques for obtaining the detailed analysis for when we have a monodispersed jet, but for polydispersed, it can only provide us the mean value, not really, details. So with the simulation, we try to see how to provide basically, further information regarding the physics happening. So we focus on only Reynolds 10,000 here, although we have the results for 40K as well. So the first step was just compare measurement and simulation. So if you're looking at the velocity, this is again, with the measurement, we can only measure the mean value. So we can see there is an excellent agreement with the PDF and experiment. There's a slight difference at the, near the jet, which could be relevant to the boundary condition. Then if you're looking at the concentration, we can see the trend captured really well, although there is a difference in further downstream. So the symbol shows experiment and the line shows the simulation. So in this, study, we consider a much wider range of particles. So the particle size is from 1 micron to 135 micron. It's much wider. It's much, better to assess the ability of the model for capturing the physics in polydispersed jet. It's interesting to see, a hump. If you're looking at the concentration, it's a very small hump, but it's captured with both simulation and and experiment. The reason for this hump is the combination of the particle axial deceleration and radial migration of particle from jet edge to the center line. That we have a concentration at about 5.7 diameter away from the jet. The reason for this discrepancy, we think, is not just because of the necessary simulation. So this could be, contributed to the measurement. The measurement there's bias in experimental measurements. So we here measuring the pseudo concentration toward a larger particle size, and because of that, we see basically this is due to the limited dynamic region of the camera. Which may result in some loss in signal from a smaller particle, and that's the reason the concentration is lower from the measurement. But the aim is to provide further information in such flow. So now we only focusing on the simulation. So if we looking at the simulation results here, the first figure at the left shows the velocity for each particle size or inlet Stokes number. So we can see that particle with the greater Stokes number, they have a lower axial decay rate, which is expected because they are less responsive to the flow. If you're looking at the small figure embedded in the first one, we can see there is at the far field, we see a trend become linear. This confirming self-similarity in the velocity profile, which is something observed in monodispersed cases. And if you're looking at the concentration, we see the huge difference between different particle size or different inlet Stokes number. At the first 2-3 diameter downstream from the jet exit, we see the constant particle volume concentration, but further downstream, the results are quite interesting. When the Stokes number, inlet Stokes number is between 0.3 and 9, we see a local maximum. This hump is the result of the, as I explained, in the previous figure, it's the result of deceleration and also radial migration of the particle from jet edge. And then if you're looking further downstream for the for the larger particle size, we can see that these harm eventually disappear. Again, this is relevant to the the fact that the larger particles are less responsive. So we also want to see how are the differences between the monodisperse and polydisperse. Again, we have the same size distribution, but we want to compare them with the monodisperse. It's another key benefit of the simulation. We can easily do that by turning off the source term in the momentum equation. But if you want to do it for the with the experiment, it's required to repeat the experiment for each particle size. The impact of the two-way coupling or momentum feedback is quite significant. If we're looking at the lines representing the results from monodisperse and the symbols representing the result from polydisperse. So it's interesting to see that the larger particle and the black line represent the alias or single phase. The larger particle velocity is higher than the gas phase velocity. In the far field particularly, this is due to the effect of inertia. When the Stokes number is small, less than 0.3, we can see the effect of the larger particle on the gas. If you're looking at the green symbols and green line which basically falling or become very similar to the alias. So because in the two-way coupling we have a larger particle, and those larger particles have an impact on the carrier phase, it's eventually, affect the dispersion of those particles. Everything is same here. The only difference is that we have a two-way coupling. And similarly, we can see the impact of the smaller particle on the larger particle. If we're looking, for instance, at results for the 5.5, we can see that the velocity for the monodisperse is higher than the velocity for the polydisperse. This is because sorry for the mistakes in the notation. The purple one is result for the 5.5. So we can see that the polydisperse, they have a lower velocity further downstream. This is because smaller particle effectively increasing the inertia of the fluid phase that affects the larger particle. And when we move into the very large particles, so Stokes number 25 or 9, we can see the difference between the mono and polydisperse become small because they are less get affected by the carrier phase. This impact is also, very clear in the concentration or volume fraction. So the interesting was the result for the Stokes 5.5. Although we see the trend in the velocity was different, but here we see that the monodisperse shows higher concentration in the far field for both, 0.3 and 5.5. This is due to the RMS velocity. In polydisperse case, the radial velocity RMS are higher, which means these particles, they were more pushed away from the center line, and that's the reason they have a lower concentration. At Stokes number 9 and 25 in polydisperse, we can see that they were more slowed down by the carrier phase compared to the monodisperse, and hence they have a higher volume fraction. Although in the velocity we haven't seen a huge difference in between the monodisperse and polydisperse for larger Stokes number, in concentration we see there is a significant difference. I also like to quickly present some results relevant to the biomass pyrolysis. These results are not based on the approach that I explained. It's actually Eulerian method, and the simulation also done by Fluent, but I thought it's relevant to this talk, so I thought it's good to present. So very quick introduction on biomass fast pyrolysis. The reason we are interested because biomass is eco-friendly energy source. They significantly produce lower SO2 and CO2 and particle matter, and they are a great source for the product actually coming from the biomass, such as bio-oil. They are a great source for heat and power in boilers, supplementary fuel in a gas turbine and diesel engine. Particularly, biomass is very popular in some countries such as Sweden, because they have access to biomass sources, and also it's a very cold country. So there are a lot of research happening in biomass and gasification. And, we worked with them on, a couple of projects. So there are different techniques when we're talking biomass fast pyrolysis. So first of all, it depends on what we are interested. So there are fast pyrolysis, slow pyrolysis. Here, the focus is on a fast pyrolysis. The reactor could be bubbling fluidized bed, agar reactor or canonical spouted bed. So they are a popular reactor considered by different research groups. We study and simulate all these three reactors, but the focus or the result I'm going to present today is relevant to the fluidized bed. So the case that we consider, so to do model validation, the configuration shows here. So we have the reactor initially packed with sand particle. So the sand particle actually packed to a certain height, or which act as a carrier, and then we have biomass injected from the left side. So the nitrogen is injecting from the bottom, which is the carrier gas. So it's the oxygen-free combustion environment. And we have a certain size for the sand diameter, initial packing, etc., which are provided here. Okay. The method or the framework for this one was to first do a CFD analysis, to do the model validation, understand the impact of operating parameter. If I just back to this slide quickly, this is a highly nonlinear problem. So we have a reactor, and the goal is to enhance or increase the bio-oil production. But it's a nonlinear function of operating parameters. For example, the nitrogen velocity, the wall temperature, the biomass particle size, the sand particle size. So all of them have an impact on the bio-oil production. So in this study, we were interested to first understand how this parameter affecting the bio-oil production, but also coming with more faster approach for the prediction, and also for the optimization. So the first step is to establish, the CFD model. As I mentioned, we're using ANSYS for the simulation, but then we want to feed this CFD dataset to the machine learning algorithm, which I will, explain in the following. So for the CFD analysis, we just use a multi-fluid model based on the kinetic theory of granule flow. It's a high-loaded flow, so obviously Lagrangian method is not suitable, so we're using our linear method. It's a three-phase because we have sand particle, biomass, and gas phase. The way they actually interact, so there is a mass, momentum and heat transfer between the biomass and gas phase. Sand particle, they're not reacting, they're just acting as a heat carrier because the heat capacity of the biomass is very low. So that's the reason sand particle required as a heat carrier. And there is a momentum heat, transfer between sand particle and both gases and biomass. So it's a laminar flow. The Reynolds number is very low, and using superimposed reaction kinetic based on a multi-component, multi-steps reaction kinetic for combustion, basically chemistry. We did the validation against the measurement data, and we can see the agreement is quite, satisfactory. For example, if you're looking at the condensable oil, the percentage of the difference is 13%. Now we take this model to do a parametric study. So we're looking at the impact of different parameters, all the operating parameters that we think affect the result, such as temperature, particle diameter, nitrogen velocity, injection height, sand particle. So as I said, the first aim was to understand the impact of this parameter, and then also to establish a data set that we can use for data analysis. I'm not going into details of all of these results, but just provide some insight. If we're looking at the temperature, we can see in the first graph shown by red symbols and line, representing the condensable oil. As I said, we are interested in condensable oil. We want to maximize it. So as we see there is a increasing, decreasing trend. This is because of the impact of the temperature. So it accelerates the volatilization of the biomass as well as the primary reaction rate. At temperature above, 525 degrees Celsius, we see the bio production start decreasing. This is because the secondary crack, starts happening, which converts condensable vapor to the non-condensable gas, and this is not desired. Or if you're looking at the particle diameter, the trend we see, the condensable, oil, we see this slightly decreases as the biomass particle size increases. But the impact is not very significant. And we can overcome with this if we use, the use of coarser biomass particle usually is acceptable if we provide the heat, sufficient heat for the biomass particle. The thing is that some of this, parameter, it's not very attractive to the industry to change. For example, the biomass particle, they getting, already graining biomass, and putting, more energy or effort to make them finer is not necessarily something they are desired. And this result shows, okay, the impact is not very huge. And what they really need is to come up with, better, provide, enough heat if they're using larger particle. We also look at the nitrogen velocity. So we can see the higher the gas velocity, the higher the condensable oil is. This is due to the shorter resistance time and also less chance of the secondary crack. But we did a further study, and there is also not presented here, but there is also, optimum point. So after, certain point, we will see the product yield start decreasing as we increase the nitrogen velocity. We have also limitation, depends on the height of the reactor. So otherwise, the biomass particle just get to the end of the reactor without actually, without devolatilization or producing any bio. So we have this data set. The way we do the parametric study was basically looking at the impact of, each parameter while we considering other parameter constant. But for the machine learning algorithm, to ensure our data set is not biased and also we have sufficient data, we did further simulation while the input parameter randomly selected. So in the second part of this work, we use machine learning for two purposes. First, come up with faster tools that can do the prediction of the bio based on the input parameter without doing CFD calculation. And second was to do optimization. So for the prediction, we use support. There are different, regression model that we can use. As I said, multiple objects, nonlinear function of the multiple input. We use support vector regression, and for the optimization, we use actually PS. Then we feed the outcome of the machine learning again to the CFD simulation to see how the CFD prediction is in agree with the optimization result. So if you're looking at the table, so the base scenario, which was, the test done by experiment, is provided here, and the optimized value are given here. It was interesting to see how some of the parameters selected in the for the base case are suitable, but how other parameter are required to be changed. Then we get this optimized value and put it in our CFD model to see to kind of validate the optimization tool. And it was interesting to see the results. So we can see that for the if you're looking at the machine learning algorithm output, the value predicted by condensable oil is about 7.7%, and CFD provides 73.4, which is quite close. Non-condensable, very close. The only difference was for the unreacted biomass, that there is difference between CFD and machine learning algorithm. But generally, it's quite good, confirming again the accuracy of the optimization tools. And this figure shows, for example, if you're looking at the temperature, how optimize solution or parameter enhance the bio-oil production and also minimize the non-condensable. So optimization is to maximizing the condensable oil, minimizing the non-condensable, and also the charge. Thank you very much for your attention, and I'd like to acknowledge all the funding through this year's. Please let me know if you have any question.
Thank you, Fatemeh. I will first introduce first question for you. The first question from audience, from Henry Liu. Thanks for your presentation. It is very informative and inspiring. I have a question regarding the two-way coupling and the breakup of droplets in Lagrange. I work in the field of first suppression, and often we ignore the droplet secondary breakup, and we find the two-way coupling effect sometimes not as significant in fair suppression studies, especially when droplets lose its momentum quickly as their sizes are small. Can you please further comment on the significance and advantage of having this considered in the model in scenarios of small droplets? Many thanks.
Thank you very much, Henry. Okay, I think it's a very interesting question. We haven't tested the model for fire suppression, but I think what you mentioned in terms of the secondary breakup, I understand when it comes to the fire suppression, the key is to come up with enough flux. So and evaporations happen very quickly. But I believe the challenge is that what we really need to capture is the dispersion of the droplet. This is the phenomenon important in either fire suppression system or other cases. So although the heat flux is the key for us when it comes to fire suppression, but if we cannot capture the droplet dispersion, that would be problematic. Particularly if we're talking about depends on the application, obviously, but this is, let's say, for at least lithium battery, when the runaway effects important, is not just about getting the right flux, it's also about the two-way coupling impacts, basically carrying out the dispersion. In terms of the two-way coupling is important or not, I think it really depends on the droplet size. But I believe for the fire suppression application, it's a two-way coupling regimes. I know, again, we haven't applied. I cannot comment on that how it works, but I believe it's have an impact on the droplet dispersion and eventually the final efficiency of the system.
Okay, thank you, Fatemeh. And also thank you for the question from Henry. The second question is from Huang Wei. Hi, Fatemeh, thanks for the nice talk. Here turbulent flows are started. For the PBE equation, should we need to filter the PBE equation, hence a subgrid will be present?
Well, yes, actually, when we applying, that's the reason we actually use the probability density function. So in a turbulence flow, it's if we want to solve the PB, it's a continuing equation. And if you want to solve the PB or population balance equation, similar to other instantaneous equation, we need to filter and somehow address the subgrid appears in the model. If you're looking at, for example, the source term at the equation or evaporation term, all of those, the interaction between the dispersed phase and carrier phase is important. So due to this interaction, the subgrid become significant, the importance of the subgrid. So when we're using filtering the PV equation, become much more complex to solve it. Similar to, let's say, for example, a species transport equation. So we have a nonlinear source term at the equation, and that's the reason we use a PDF version of the population balance equation. So mathematically, the PDF allows us to resolve or have a closed term for the source term, although it's introduced other challenges. For example, in the combustion application, the challenge is mixing. In our scenario, the challenge was inertia effect.
Okay, thank you very much.
No worries.
Okay, the second question from maybe I will ask question following this. Fatemeh, I know you you introduced a very fancy Stoker spin method. But I would ask from the, for example, I know similar algorithm or regime for the number density based on the droplet size. When we study the number density of droplet size, sometimes we say the number density per volume or the number density per mass. I'm not sure, is there any similar regime exists here for the Stokes numbers?
Well, to be honest, I think when it comes to the number density, I think the term number density is different from number. So, for example, drawer method, they're talking about number of the droplets. This is a number density and it's the a continuous function. So I think that's the difference between this method. So number density or population balance equation is the continuous equation. Or when we're talking about number of the particle, it's not necessarily continuous. That's the one thing, and it's not the mathematical framework, I think, basically become different. So for example, I think the paper by Jones, they provide a PDF equation for the number of the droplets, not number density. Mathematically, they are different, although there are some similarity in terms of the stochastic equation that we solve at the end. But the mathematical concept of framework is initially is not the same. So number density allows us to consider a wide range of parameter in the property space. That's I think one of the the benefit, and particularly become powerful when we have a nucleation or we are interested in the morphology changes. Did I answer your question, Boysen?
Yes, thank you. I think I made a small mistake just now. It's the number per volume or number per mass. Sorry. Yeah. And the second question from Huang Wei, also for the first case, the inlet turbulence is high, 15%, if I'm not making a mistake. I guess the particle dispersion effect by the turbulence will be strong at the inlet. Did you consider this when you inject particles? For the particle distributions you present, this is not very obvious. Thanks a lot.
So in the first case that we did the simulation, so I think we consider 50%. Usually for the turbulence jet, it's 10% to 50%, at least what we found at that time through the literature. So the value we assign actually to just for us for that simulation, I agree with you, the turbulence intensity become important, but depends on the scenario. We actually did further study for the bluff body configuration, but for the jet flow, our focus was to do model convergence, see how the model is capable to capturing, looking at the different numerical aspects of the model. The study was actually published by JFM. That's the reason we didn't do any, we didn't look at the impact of the turbulence intensity. But in the bluff body configuration, we did that. And we found what is happening because turbulence boundary is quite challenging when it comes to the multi-phase flow, particle-laden flow. So what is common in the LES community depends on the experiment as well. But in experiment, in reality, they have a long pipe and they injecting particle with the gas in the long pipe, and then they do measurement for the jet. So if people want to do pipe particle simulation, it becomes quite time consuming because it's going to be a four-way coupling. So the interaction between the particle and the walls become significant. So what is common to do is to inject, to have a pipe simulation, pre-simulation, just for the carrier phase, and then assign particle to the domain with the carrier phase velocity. It's not necessarily ideal, but we did this sensitive analysis or looking, okay, is it important to consider a better distribution for the particle when we're injecting them? In the bluff body, what we found, it's important and it has an impact at the initial or close to the injector, or further downstream, it's become insignificant. So in this study we published in International Journal of Heat and Fluid, we show that different type of boundary condition. For example, you're injecting particle with the constant velocity regardless of their size. You're injecting particle with the carrier velocity. You're doing, you're extending your domain further upstream to have a better distribution at the jet outlet. So we did this sort of, analysis. At least for that configuration, we found the impact is just important at the close to the injector.
Okay, thank you.
No worries.
Okay, it seems another question from audience. From OpenFOAM, thanks for your next talk. I want to know how is the performance of your method in supersonic flow? Is the droplet model suitable for supersonic flow? Thanks.
Thank you. I think it's a very interesting question for the supersonic. Obviously, we focus on a subsonic flow. I think the mathematical framework should work, but obviously, we're dealing with the different sort of challenge. I think the key is that we considering the mathematical framework, or the model, the way it's designed is to consider the effect of inertia using Stokes. As long as this is a valid assumption, we can use the model in other flow. But we haven't tested. So I think it would be also very interesting to study on how it's going to work in the supersonic flow, because I think probably we may need consider more than just the Stokes number for our as a criteria for our model.
Okay, thank you for your answers. And I think the next is my question. Although I know this this method since several years ago, and I'm still not know well about the implementation about the Stokes spinning. Could you please explain about it?
Sure.
I mean, in OpenFOAM, what I know is when we use Monte Carlo particle method, we solved for the PBA equation we solved particle size, or no, we solved the number density on the particles. But I think you must have the Stokes numbers on the particles, and also have the particle size on the particles.
Yep.
So what is the logical correlation about them, and how is the Stokes spinning is involved in this structure? Yeah.
So thanks, Mohsen. So I think the way we actually implemented in the code is to just try to ensure the Stokes number for each stochastic particle is sorted. So we always, sorting that. We know the first is the lowest, the last is the highest. So that's the way, we're sorting. So it makes, the comparison with the the Stokes spin much easier. So once we did that, we updating a Stokes number or the Stokes range for each notional particle as the droplets evolve. The way it updates based on the particle response time, and also the carrier or the flow response time. So there are also, discussion how we're going to define the carrier or flow response time. So there are different methods, different, study proposed different parameter. For example, one could be based on the large eddies. In jet flow, it's quite common to consider the flow response time based on the large eddy. The way we do it is to calculate the large eddy, so using pre-existing LES data that if assuming we have a shear layer and you can capture the large eddies, and then you calculating the size of the eddies, and then you're going to finding the time, equivalent time based on the the velocity. So the location of the notional particles, so the carrier velocity, you can easily calculate the response time. And as I said, the particle response time is can be just obtained through the drag force and slip velocity. That's what we do. So once we have that, we have updated Stokes range, and we always sorting in a way that it's from lowest to the highest, and then we comparing that range with each Stokes spin. It's the number of Stokes is actually usually 8, is very low, so the search is very quick. So when we did that comparison, we identifying, the stocks that the bins that this particle might fall in. So if it's falling in one bin, it means we're satisfying the criteria. But if it falls in two bins, it means we require to be split. And based on that, we split the stocks. The notional particle.
So the bins are dynamic adapted.
The bins they are established prior to the case, so the bin size are fixed, but then the Stokes range for each notional particle is variable, is dynamically adopted every time that particles evolve.
Okay, thank you. And the next question is about your system. I know you introduced the breakup, and I'm not sure you introduced the breakup. Have you introduced the coalescence of the droplets in the system?
No, that's something we haven't considered yet. Yeah, that's definitely important, but at this stage we haven't included coalescence.
Okay, so when you compare the your result with the experiment, you usually compare the volume fraction or the size distribution?
For the breakup case, it was very simple to just demonstrate how the model works. So we actually comparing with the point particle result node experiment, and that's for the breakup that we did. So we actually working on a comparison with the experimental result for the spray flow, but we haven't completed those results yet. So, but the result that I just presented, they actually comparison between the PDF-PB and droplet simulation, which is the basically point particle simulation.
Have you compared? Maybe you showed in the presentation, but I cannot remember. Have you compared your result with the droplet size distribution from some experiment?
Not for the breakup. No. Not for the breakup. Only for the dispersion. So
only for the dispersion.
Yeah.
Okay. And the next question about the how to distinguish the regime from the primary breakup to the secondary breakup, and from the second breakup to the non-inertial flows. I know this is a very very difficult problem, and no one can explain it well. I mean, as I know, but I know introduce a Weber number for the breakage, right? And also you introduce, let's say, the ligaments and various droplet shapes in your simulations. Or maybe I make it focus. Let's say when you consider different shapes of fragments and also ligaments, how to you still have do you still have a characteristic size for this kind of shapes, particular shapes?
I think it's a very interesting question, and it's a very complex, challenging, to address. When it comes to the coming with the breakup model, so I think generally we're talking about the spray flow. We have a number of challenges in terms of the simulation. One is coming with the framework that can address primary, secondary atomization. At the moment, the existing model, for example, ELSA, they making assumption to provide the transition from primary to secondary, but the challenge is that they are not considering shape particle, or they're only focusing on the secondary, or they only focus on the primary. So it's still there is a challenge to come up with a model that works for the both primary and secondary regime. That's the first things. But the fold density function in principle can provide that framework for us. So, and then the mathematical framework, once the mathematical framework is available, is more about, okay, how we want to actually do the physical modeling. Breakup modeling by itself is a physical phenomenon, which is again challenging, to capture. So there are models represented, which is the function of the Reynolds number, Weber number, the more advanced model, they considering the probability of the daughter droplets produced from notional a mother droplet, for instance, in assuming a droplet will be identically break to the break to two identical droplets is not necessarily a valid assumption. So draw also models to come up with the probability of the produced droplet. So I think we need to keep in mind are two different issues. So the first one is relevant to coming with the framework for the whole flow. The second one is what is the best model that can address that. Obviously, coming with the model capable to do all of them, it would be fantastic. But I think at this stage is still challenging. And to answer your question, how we can distinguish this regime, ideally we want to have a model that doesn't need to distinguish this regime. It eventually works from the primary to the secondary without compromising the accuracy. The method like ELSA, what they do is basically consider all the breakup in the combining the secondary and primary together, do the breakup based on the instability in the surface, and then assuming there are fine droplets, which is the dilute regime. So that's what ELSA does. So ignoring the secondary and the primary. So here we want to come with the framework at least resolve this challenge. But in terms of what are the physical breakup, I think that's something we need to work on it.
Okay, maybe the final question from my side. I remember you showed a result for different Reynolds numbers for the droplet disperse and also breakup. I think for the lower Reynolds number, you got a good result agreement, and for higher Reynolds number, it seems the discrepancy occurs in the downstream.
Yep.
Does it mean in the high turbulence flows, the breakup happens more frequent, and very small droplets are in the downstream, and your model cannot capture that? Is it?
I'm not sure if it's the scenario is necessarily the model. I mentioned that I think there also uncertainty associated with the measurement is another challenge. We check what we check at that time was mesh, because we have a higher Reynolds number, so maybe the initial mesh wasn't suitable. We see also for that particular case, we see discrepancy between single phase. If I particularly for the velocity RMS, we saw discrepancy. The reason is that for that particular experiment, the data was very limited, so we didn't have a velocity at the jet exit. That was a challenge, so we couldn't really ensure if the boundary condition or the initial condition are captured well. We only have the mean velocity and RMS along the center line. So, and we see the discrepancy for the RMS, which I think it's contributed to the discrepancy when seeing for the higher Reynolds number. So the mesh boundary condition, basically LES or the single phase, could be also a source of problem here. And the other challenge or the potential source of uncertainty is the measurement. So at least the measurement shows same displacement for further downstream for both 20K and 30K Reynolds number, which is not true, which is not valid, and that's the reason we think it could be. The uncertainty is about 12% presented, and our value falling in that range of uncertainty.
Okay, thank you, Fatemeh.
No worries.
So I think there's no questions anymore, and I suggest all the panelist members can turn on the camera, and we say goodbye, and see you next time. Yeah, Huang Wei.
Yeah, thank you, Fatemeh.
Thank you very much. Thank you for the invitation, and thank you for joining in a very late time.